Okay, so Unit 4, we're all about triangles in this one. As we begin, quick review over what triangles, like how we can classify them, the different aspects of a triangle. We have three things that you probably are familiar with and one that you might not be. So if we look only at the angles of a triangle, if I have three acute angles, well then my triangle is going to be an acute triangle. Every angle is a cute little triangle, cute little angle. If I have one obtuse angle, meaning an angle more than 90, okay, one obtuse, well that overpowers the bunch. So the whole triangle is going to be called obtuse. If I have a right angle, then the triangle is called a right triangle. And then if I have three angles that all of which are the same, all of which are equal, and I know they're equal because of these arcs that tell me this measure is the same as that, it's the same as that, then I have a triangle called equiangular. Okay, equiangular. That just means equal angles. That's all it means. So we have three normal types, acute, obtuse, and right, and then this special one that might be new to us this year, equiangular. So if we go down here, classify each triangle by its by its angles. Okay. Well, looking at the yellow one, CDE, I see I have a right angle there. So that box will tell me that this is a right triangle. BCE, BCE. Well, I have one angle that certainly is obtuse. This C angle right there, that is bigger than 90. So that's going to taint the whole thing. The whole triangle is obtuse because of that one angle. And then ABE, ABE is this right here. I see three arcs in the corner. Every one of those angles are the same. So I'm going to have an equiangular triangle. Now, of note, if you have an equiangular triangle, all of the measures will always be the exact same thing. Obviously, like that's the definition, but sure, but like it's actually like mathematically the same. Each triangle, every triangle in existence has 180 degrees inside of it. That's a fact, it's not going away. But if I take those 180 and I split it evenly from three corners, each corner is going to get 60. So this one is 60, that one, and that one. That never changes. That's a fact. If you have an equiangular triangle, everything is always 60. Now down here, we're going to talk about triangles based on their sides. And again, there's probably some familiar words here. Maybe there's a new word. If I have three congruent sides now, sides, equilateral. Okay, so same side, equilateral. Lateral is just like a, I don't know what the root of the word is, but it basically means side. Like quadrilateral means four sides because quad is four, like a four-wheeler. Quadrilateral, equal sides. If I have two sides that are the same, just two, then I have isosceles. And then if there's no information, scalene. Okay, if I can't tell for sure, scalene. Even if I really thought that like maybe this side was equal to this side, maybe it looked like it was the same length, but there was no tick marks on it like this one, don't assume, okay? You have to go by the information that they give you, not what the picture looks like. So if we look at these triangles based only on the sides, the blue one, I have a one tick mark on this whole side, a tick mark plus some, so I don't know how long that is, and then a two tick mark plus some more. I don't have enough information to say that one side is the same as the other, so I'm going to call that one scalene. The yellow one, two tick mark, one tick mark, two tick mark. Okay, well I have two sides that are the same for sure. That's an isosceles triangle. And this one, the last one, one tick mark, one tick mark, one tick mark. Okay, everything is the same, so is equilateral. Okay. Of special note, the equilateral and equiangular ones, they always are the same. You can't have an equilateral without having it also be equal angular. It doesn't exist. You can't, like, due to the rules of triangles, the equals have to go together. So if it's equilateral, it's equal angular. If it's equal angular, it's also equilateral. And we just talked about how each of these will be 60. Now the sides can change. Sides can be really small or they could be as big as a pyramid, but the angles will always be 60. Okay. Put it together. Classify each triangle by its angle and the sides. All right. This, if I look at the angle first, it has a box right here. So that's going to be a right angle. If I look at the sides, I see one tick mark, another tick mark. That's two tick marks, so it's going to be two equal sides, isosceles. So this is a right isosceles triangle. This one, let's look at the angle. It's bigger than 90. Bigger than 90 means it is obtuse, and all you need is one angle to be over 90 for the whole thing to be obtuse. And then if I look at the sides, I don't have any tick marks, nothing here, no information. So I'm gonna have to assume that it's scalene. And then the last one. All right, well I have three equal angles and I have three equal sides. Again, I can't have one equal without the other. So this is an equal angular and it's equilateral. Couple more. Let's see here. Well, if I look at the sides, I don't have any matching. So that's gotta be a scalene triangle. But what about the angles? I don't see a box, so it's not right. I don't see my little arcs to tell me that all are the same, so it's not equal angular, but I knew that because the sides weren't equal anyway. It doesn't look like I have an obtuse, so it's gonna be acute. All of these angles are less than 90. Here's a box. So it's a right triangle. And I don't have any tick marks or measurements or anything. I have scalene again. And then here, I have an angle that's bigger than 90, so it's obtuse. And even though I don't have tick marks, it tells me this side's 5 and that side's 5. I could put tick marks there if I wanted to. But I know that it's isosceles because I have two sides that are the same. Okay. PR bisects the blah, blah, blah. Oh my goodness gracious, there's a lot happening here. Okay, let's pick it apart. Suddenly it was all nice and easy, and now this. PR bisects SRT. Well, let's find PR first. PR is this line here. And it says it is bisecting angle SRT. Well, S is here, RT. So this is cutting this in half. I know that this piece is going to equal that piece. Okay. So I use this. U is the midpoint of RT. U, where's U? U's here. U is the midpoint of RT. RT is this whole thing. Okay. So U is right in the middle. Right here, this half of this line, UR, tells me it's 8. So I can put this little tick mark over here just like that, and I can say that this is 8 as well. Okay, I use this, and then that's it. No other labeling information. It gave me this bisect for a reason though. I can probably use that. So if this yellow line is cutting this whole thing in half, this piece of it was 30. Well, that tells me that that other side is gonna match it and also be 30. Okay. Now I drew all over this picture. I don't want to highlight over it again because then I'll have to erase stuff. So let's just try to follow U, Q, R. U, Q, R. We're trying to do angles and sides. So UQR is this triangle here, this one in this bottom corner. Let's talk about the angle first. I have one angle that is bigger than 90, so this is obtuse. But what about the sides? In this tiny triangle right here, I have one tick mark and one tick mark, and then nothing over here. That is two equal sides. Okay. RST. RST is this big old thing. It's this entire piece right here. Okay. So looking at the angles, this corner was 60. This corner was 60. And then this corner was a 30 with a matching 30. So the whole thing together is 60. Okay. Equal angular. I don't think there's an A or L in that. I could be wrong. And we knew for a fact, right? We just talked about it. If it's one equal, it's the other equal. So it's also equilateral. We can prove that by coming back and saying, okay, this is 16, this length is 8 with another 8, and then we labeled this one 8 and 8 down there. Everything is 16. SRQ. So now we're talking about SRQ. So, okay, so it's this one right here, this one. It has a right angle box. What about the sides? I see I have an 8, a 16, and then not enough information here. It doesn't give me anything, and I can't figure that out easily, so I'm gonna assume that has to be different. I have no matching. PRT. Okay, PRT is this big one over here. PRT, it's this whole thing, okay, ignoring this piece. At the angles, I have one that's 30, one that's also small, and then this one here, this has to be over 90. Like, look at it. It's gotta be. So it's gonna be obtuse. But what about the sides? Okay. I have one that is 16. I have one that is 8 with another 8, so that matches, that's another 16. And then this big long one, I don't have any information about, but I have two that match. So that's gonna be isosceles. TQU. TQU is this tiny one right here. Okay. I got 160, one that I don't have any information about, and then one here that I don't have any information about either. But I do. But let's say I didn't figure that out right now. I didn't know that relationship yet that I will talk about in a second. Ignore the angles. Let's look at the sides. This side is 8. This side is 8. Well, I gave sides with 8 a tick mark. So can I give that one a tick mark too? Sure. Tick mark, tick mark, tick mark. 8, 8, 8. It's going to be equilateral. Which should inform me that it's also equiangular. But let's prove how it is equiangular. This corner was 60. Yeah, that was true. But this one over here, I can prove that that's also 60. Because what we have is we have a thing that looks like this. This part of the triangle, then 120 over here. Well, this angle here, you know, straight lines are worth 180. Had to be 60. So if this is 60, that had to be 60. And then triangles are also worth 180. I could take away the two 60s from this corner and that one to figure out the last one. And yeah, that would end up being 60 as well. Okay, last one, PQT. PQT. It's this one right here. I have an 8, a 16, and then I don't know about that side length. 8, 16, I don't know. So it's gonna be scalene. But what about its angles? Okay, don't know. don't know. Acute though, acute. What's this one doing? Is it less than 90? Is it more than 90? It's actually equal to 90. See how there's a box over here? Well, this angle is vertical to that one. So there's a box over there too. Okay. All right, I think these are the last couple ones. Both. All right, it's not too long. All right, finish up this page. Find the measures of the sides, then classify it by its sides. Okay, everyone's favorite part. We need to use the distance formula. The distance formula was this: distance equals the square root, you remember this from unit 1, x2 minus x1 squared plus y2 minus y1 squared. It was your favorite. Okay, but that's what I have to do. And I have to do it not once, not twice, but 3 times per problem. Oh, the best. Okay, I need to take J and K. I'm gonna pair up these two right now because I can only work with 2 of these at a time. So I'll call this one x1, y1, x2, y2, and I'll do this first one. Distance equals big ol' square root. x2 minus x1, negative 9. Whoa, wrote that terribly. What am I doing? Negative 9 minus, because the formula says minus x1 minus 7 plus. Nope. I'm messing this up terribly. Terribly, children. Terribly. I don't know what day it is for you, but for me it's a Monday, and I think you can tell. All right. Parenthesis, how about we do that first? Negative 9 minus negative 7 squared plus parenthesis y2 1 minus y1 squared. Okay. All right, so now that I've actually written it correctly, let's make sense of this a little bit more. Negative 9 minus a negative. When we subtract negatives, they turn positive. So negative 9 minus that is going to be minus 2 squared plus, more subtracting of negatives, so it's going to turn positive. 1 plus 7 is 8 squared. 2 squared is 4. It doesn't matter that it's negative. Everything that you square will always be positive because it's saying negative 2 times negative 2. Negative times negative is positive. So 4 plus 64. Okay, that one's done. I gotta do that 2 more times to compare these final answers. Remember, leave it in the box. Don't take it any further than this. Okay, let's pair up the next one. I'll call this one x1, y1, x2, y2, and I'm going to do the distance formula a second time. Big ol' square root. I'm going to write it similar to this for the first one here. Like I'll do this whole problem that way. Okay, x2, that was here. Negative 1, formula says minus x1. x1 in my green scenario was negative 9. Plus y2, negative 1. Formula says minus y1 here, and this green one is 1 squared. Okay, subtract a negative turns positive. Negative 1 plus 9 is 8. Negative 1, take away another 1 is minus 2. And maybe we can see that we have the same numbers that we had here. Okay, so at this point, I have 2 sides that equal each other. This triangle is already an isosceles by default, 2 equal sides. If I get a third 68 though, then it's going to be equilateral. So I for sure have isosceles, but we need to figure out equilateral. All right, I paired up these two, I paired up these two. The last one I have to do is pairing up these two. x1, y1, x2, y2, and we're gonna do this a third and final time. x2 in the blue scenario is this one. Formula says minus x1. That is a 7. That is a 7. Plus, parentheses, y2. In the blue, formula says minus y1. Maybe I shouldn't do that cross here. Okay, close it up, parentheses. All right. Simplify it a little bit. -1 minus a negative turns positive, so that's going to be 1 plus, or -1 plus 7. 6. That's a different number already than what we've had before. Same deal over here. -1 plus 7, 6. So I have a triangle with a side that is 68, a side that is 68, and then a third side that is 72. I see two sides that match. So the whole triangle is isosceles. Okay, one more. Here's my formula. I'll start with pairing these ones up again. x1, y1, x2, y2. Okay. All right, let's see if I can shrink this up a little bit, do this a little bit nicer. We still have to start x2 minus x1. Now I'm going to put a minus and I'm going to put x1. Subtract a negative turns positive. Doing the same thing that I did before, I'm just skipping the step of writing the double negative. Plus y2 minus y1. Okay, no sign change there. Okay, so I have square root of 41 for that one. Okay, x1, y1, x2, y2 for the green one. x2 minus x1, no sign change needed. y2 minus y1, no sign change for that one either. -1 minus 6 more. Remember, anything squared becomes positive, doesn't matter. So what I have now is two sides of a triangle. One is square root of 41, the other is square root of 85. They don't match. Isosceles isn't off the table. Maybe side 3 will match one of these ones, maybe, but equilateral's off the table because these aren't matching already. Could also be scalene if I get a totally different number. All right, the last one, I paired up these ones, now I'm gonna do these ones. This guy's gonna be x1, y1, x2, y2, and the last time for a formula. X2 minus x1. So I'm gonna have 8 minus a negative. That's gonna turn positive. Y2 minus y1. Alright, some of you might already have noticed that I have different numbers than I did over here, so we're probably not gonna get a match. So I have 41, 85, 130. I don't have any matches. So all of that work to say none of these equal each other. This is a scalene triangle. Okay. You have to show all this work, otherwise you won't get all the points. Okay, we don't need to do another one of that. I think we're gonna pause there.